So this is a joint work with Erhan Bayraktar and Jenny Young from University of Michigan. Let me just start with putting the model in the literature. So it's connected or related to two class of models. One is the habit formation models, and the other one is consumption ratcheting, essentially. So let me go briefly over them. Habit formation models are really a classical topics. They started in early 70s, same time as Merton. And then I put some papers here. If you really, I would just want to get some literature there. You can read Xuan Yu paper, and he actually is the student of Gordon Zitkovich, and he had his a thesis on essentially habit formation model. So that's a good thing to go. Let me just briefly tell you what type of modeling they use, because I will be using some terminology there. So, there's an optimal consumption problem, finite horizon, infinite horizon. T can be infinite essentially, and then you will have like a utility function that essentially you get the utility not from consumption itself, but consumption in excess of some reference point. And then the reference points, like the standard of living, is essentially an exponentially weighted average of your past consumption. So it's a running average of your consumption. There are two types of habit formation. There is addictive habit formation, and then there is non-addictive habit formation. And the difference is whether you allow the consumption rate to be below the reference point or not, right? If you allow it to be below, it's non-addictive. If you allow it to be above, then it's addictive. Yeah, I think I'm gonna change the screen. That thing is coming. Right, and then the way it works, the way they change the habit, like essentially enforce this constraint, it's really not through a constraint, it's through the utility function. So essentially, if you're assuming that the marginal utility when c equals z, so essentially this c is 0, if the marginal utility is plus infinity, it will automatically enforce this constraint. So we can kind of to a power utility essentially. Or if you allow finite marginal at c equals 0, like exponential utility, you're gonna get a non-addictive habit formation. So that's the generally is. I didn't really explain what results they have. I just want to like explain a bit those bits that I will be using during this talk. Again, go read Shen Yu's paper and thesis to get a better understanding of the literature. Now there's a second like class of models that also relates to habit formation, and that's consumption ratcheting and drawdown. So in here, you model habit formation not through the utility. So the utility is usually the normal utility of consumption, but through a constraint. So you are essentially at a constraint that your consumption cannot fall below a proportion of your reference point. And then there's another difference between these two literature, that the reference point is now the running maximum of consumption. So it's not the running average anymore, right? Specifically, if this alpha is 1, then it would be you're essentially requiring consumption process to be non-decreasing, essentially ratcheting it up. So that was the first paper by Divig in 95. Let me just show you the paper. Yeah, this is the one, right? And then, later on, Aaron is like a PhD student of Mike Terhanchi. He essentially extend the model for alpha between 0 and 1. So essentially, you can think of alpha equals 1. You're not allowing C to go below ZT, so it's going to be the addictive case, and alpha between 0 and 1 is going to be the non-addictive case. So that's the kind of relationship. There are other people contributed to this literature. So Junko and Shin have a lot of papers on this line. Like specifically this paper extended. So these two papers are infinite horizon. T is infinite. They extended to finite horizon. And then we essentially extend the problem to the case where bankruptcy is allowed. So this this case, the original cases were essentially under no bankruptcy condition. Aperture and his collaborator also have a couple of papers which is similar to us in allowing no bankruptcy, but it's a different setting in more like Brownian essentially loss model setting. And then finally, Deng Li Pham and Shun Yu also have a recent paper where essentially they consider the same type of model, Z is the running maximum, but instead of introducing the constraint, they're doing the habit formation through a utility, like a habit formation utility. So essentially they keep this preference, but their Z is the running maximum instead of the average. Okay, so these are like the related literature. So let me go and like place our model now. So the motivation here is that consumption ratcheting models are more tractable. They usually give more explicit type of policies. Habit formation models are really notoriously difficult, right? And then usually you get the optimal policies either in terms of some like a process that comes out of martingale representation or some solution of a PD or something. So it's really not that explicit result. So consumption ratcheting models are more explicit. But on the other hand, the reference point in habit formation literature is more realistic. So, two things, two like realistic things a running maximum cannot capture. So if I consume less, my reference point should go down. That's how it works. So if I'm used to like high consumption rate, I reduce my consumption, I consume for a while, I will reduce my habit. This cannot happen in running maximum. So once you consume at a level, that would be always your level, right? So you can only increase the habit, right? So then the other thing is that you cannot forget, right? This is like, you never forget. In reality, we forget, we conform, right? So in our model, we essentially taking the reference point as the running average, like the habit formation literature, but we model the habit formation mainly through a constraint, like the ratcheting literature. So in that sense, it's that type of hybrid. Okay, so just compare, like as I said, this paper by Deng Li Pham also have a connecting these two literature, but it kind of are opposite direction. So their choices are opposite. So their reference points is running maximum, and their habit formation is through utility. So it's the opposite of our choices. Okay, so let me just set up the model now.
Sorry, Bahman. I think our colleague Martin has a question.
Oh yeah, sorry. Yeah, please go ahead.
Yeah. Couldn't you, for the maximum, you could just discount that and sort of you say the further things are back, you take the maximum over sort of this discounted thing, but I think then it would already be as intractable as the average. Is that right?
So what you're saying is that, can I just take the running maximum? Let me find it. So running maximum and discount it.
Well, you discount before you take the discounting is inside the maximum.
Oh, but I'm not. So if you look at here, I'm not discounting the maximum. I'm discounting the consumption rate. It's different, right?
Yeah. No, but the question is, you said that the maximum of the consumption rate is unrealistic, absolutely. But if you would discount, then maybe it would become more realistic, but this is possibly as complicated as the,
So now I just want to understand exactly what you're saying. So what you're saying is that take the Z as running maximum and then put an E to the minus delta T.
No, the E to the minus is inside the maximum. So I take the maximum of E to the minus
delta DCS.
E minus S CS.
CS. Right. That's a possibility. I haven't think about that, so I should say upfront. But it's still not the average of consumption rate, right? Mm-hmm. It's still not the average. So essentially, what you well, let me think about. So what you're doing is you're taking the consumption rate, and then you put a discount rate in front of it, and then take the maximum of that, right? So essentially what you're thinking is that, oh, if I have like my maximum consumption is, I don't know, $100 a year, but it was 20 years ago, that would have less effect. It was like $100 a year, but it was last year. So this kind. Okay, so that's actually another way. So let me think whether that would. So the way you're saying it is essentially it's not going to have the complication I will be facing. So your model would be tractable, more tractable than mine. But on the other hand, you're also not changing your Z as fast as I do.
Yeah,
so,
absolutely.
Yeah,
absolutely.
So but I think mathematically you will be more close to consumption ratcheting, which is a good thing. Yeah.
Right. Thank you.
No problem. The market model is like a Black-Scholes model. So stock is a geometric random motion. Oh, by the way, before I go ahead. So what I'm going to do, what I promised you to give a talk on was the deterministic case. But I promised Kitchen to give a talk, and now we actually had the stochastic case out as well. So I just put some slides and some results, and I will be setting up the problem for the stochastic case. But my goal is mainly cover the deterministic case. If I go over time, then I will just stop here and then let you ask me about this. If I have time, I will go to the stochastic case. But at least I set up the problem for stochastic case. So, okay, so let's go ahead. So stock is a geometric random motion. There's a bond with constant interest rate R positive. Pi would be the amount invested in the stock. C would be the consumption rate. And then the wealth process is going to be given by this SD. Well known everything here. Like new part, maybe you don't know it, is the habit formation constraint. So what I'm going to do is I'm going to take a consumption process. I'm going to define its running average, which by the way, you can actually write this down as what I did here. So you can write it as minus infinity to t. So essentially you think that you've been consuming from minus infinity till now. And then the Z would be essentially the initial value of consumption habit that you have. So minus infinity to 0. In that sense, you can essentially write this down as like you're having this type of dynamics, right? Which I will be using when I want to do control. So Z is going to be your habit, consumption habit. Z0 is the initial consumption habit. Rho is how sensitive your ZT is with the consumption process. So if rho is large, your ZT will change super fast with C. So essentially, you put a lot of weights on recent consumption. If rho is small, you're essentially kind of taking the average consumption. So essentially, your ZT will be changing, will be much less reactive to the consumption. Then I'm going to add the like habit formation constraint, which is your consumption rate at any time t cannot be less than alpha as a fraction of your current habit, right? So I will think of alpha as how addictive my habit formation is in this sense. So if alpha is 0, it means that your consumption, your admissibility set is completely independent of your habit. Your habit doesn't affect your consumption. If alpha is 1, it would be very restricted, right? So if Z changes, your admissibility set immediately changes. And then alpha between 0 and 1, the smaller alpha, the more tolerant you are to consuming less than habit. So think of alpha as how addictive your habit is. Okay, so let me go forward. So now I want to stay with the no bankrupts, the case that person always try to avoid bankruptcy. So what happens is that just because you have this habit formation constraint, it will enforce a lower bound on your habit process, which is kind of not difficult to see. So essentially, if you start with a Z and then you always consume at the lowest possible alpha CU, that is going to give you an ODE for Z, and then you can solve it and see that that's going to be your lowest habit. But I have a detailed proof there. So now that you have a lowest consumption, lowest habit, then you will have a lowest consumption as well. And then you need, if you want to avoid bankruptcy, you need to make sure you can always afford to fund that from risk-free rate. And then you do this argument, and you can actually identify what level of wealth is your safe level. So above that, you can always fund this lowest consumption, right? And then what happens is that lowest consumption is essentially going to be a function of alpha, which is this guy, right? How addictive. R, your interest rate, and rho, how sensitive your habit is. So in this case, x under is going to be this number. So your wealth should be always greater than this constant x under times your habit. If your wealth is less than that, then you cannot avoid bankruptcy. So I would always assume W2T, so wealth to habit ratio is above x under. And then just to think about it, so this is essentially an increasing function of alpha. Larger alpha means that you need more wealth. And then larger R means you need less wealth, because your riskless is more profitable investments. And larger rho is also means you need less wealth, because if rho is larger, you can adjust your habit faster, so you need less wealth. Okay, generally makes sense. Now you define the admissibility set. I need some integrability conditions. I need the habit formation constraint, and I also need the no bankruptcy constraint. So these are the main three things for admissibility. And then just summarize. So essentially, you're going to have a bivariate control process, wealth and habit. And then your control is the stock investment and your consumption, right? Now, this is a good problem for later, right? This is the first paper of this kind, so I'm not going to start with a PD. I'm going to stay with ODE if I can help it. So what I'm going to do next is I'm going to start trying to think about a one variable, like a one variate process, control process. So here's what you can do is, instead of thinking about W and Z separately, think about W divided by Z, right? So W divided by Z, just apply Ito's rule, and then you're going to get an SD for it. And then you can think, well, if I call this X, I'll call it relative wealth or wealth to habit process, then it would be essentially in terms of, there's another X here. Instead of control pi, I can just work with control pi divided by Z. Let's call it investment to habit. And then instead of working with C, I can work with C divided by Z, consumption habit. So essentially, if instead of W, Z, pi, and C, I divide everything by Z, I'm going to get an autonomous kind of differential equation for X that only depends on these relative tetans. So just from the control point of view, I can actually control X by just looking at tetans. So now what the question is, if I start with a theta C and X, can I recover my W and Z? And that's also possible. So if I start with the wealth SDE, this is the wealth SDE, right? This is the same as this guy. I just divided by W. Right, so start with the wealth VSD, and then notice that pi over W is just theta over X, because essentially there's a Z in the numerator and denominator, right? And then C divided by W also is C divided by X. So if I know X, theta, and C, I know these guys. So W is just going to be a stochastic exponential of these known processes. And then once I have W, then I can recover pi and C. And once I have C, I can recover Z. So essentially goes both ways. So in other words, I could essentially start with a admissibility set that depends on C and theta only, their relative investment and relative consumption. By relative means divide by Z. And then instead of working with W and Z, I would only work with X. Okay. So from now on, my admissibility is defined over this process A. Okay, so now finally the problem, the stochastic problem itself. Okay, so here comes. So my essentially, I'm trying to maximize expected utility infinite horizon. I'm taking relative consumptions. That's a modeling choice I'm taking, because with this I can reduce the dimensionality. So I'm working with CT with relative wealth, which is not actually, from model point of view, it's not a bad thing. So what I'm saying is that I take my utility from not my absolute consumption, but my relative consumption. So how much more than my habit I'm consuming, not just how much I'm consuming, right? So, and then, yeah, so that would be this. Then I'm also introducing the delta, which plays a good amount of influence in the solution. So delta is whatever is the subjective discount rate. So essentially, it larger delta means you're more impatient. You want to consume earlier than later. Or if you want, you can think of my like our criterion as a random horizon, like a consumption problem, and then this delta is essentially 1 over life expectancy. So your time of death is exponential with lambda, or lambda is like some kind of delta, and then so your life expectancy would be 1 over lambda, right? So larger life expectancy is lower delta. So think about it that way. Okay, finally, value function is just one variable, v of x, is essentially supremum over relative consumption and investment, and then this is going to be my expected utility. Oh, so everything is nice. You might say, well, I mean, what's the difference once you did the you lower the dimension? What's the difference between this and, let's say, Merton set? And then I go one slide back. I look at my x dynamics. The source of all evil is this term, 1 plus rho x c. If it was not there, then you would be similar to what you have in Merton. But all of my problem essentially comes from this term, as you will see. Okay, so just a heads up. Okay, so now I have maybe, I don't know, 35 minutes left. So I would try to cover all the, probably not 35 minutes. We need some time for the question, but so I would try to cover all the deterministic case, and then we'll see how we get to the stochastic case. Okay, so let's go ahead. So what I'm going to do, I'm going to assume that pi is 0. So I'm going to throw away all the stochasticity in here. So the budget constraint, which is this guy, relative budget constraint, I throw this away. I'm just going to get an ODE, right? So once you have C, you can essentially have X in explicit form because it's just a linear ODE at the end of the day. So it's really not difficult. I'm going to come back later to this equation, so keep this in mind. So this is going to be your wealth process essentially. A sub 0 or A naught is going to be the new admissibility process. So you throw away stochasticity. Now your consumption rate is just a function. Is a function of t. I forgot actually to emphasize this. So your habit formation now it becomes CT greater than alpha, right? Because CT is C divided by Z. So this is the same as habit formation. Your no bankruptcy condition also simplifies. It's just XT is greater than X under. So it becomes much easier things to handle. So here it would be XT is greater than X under. Okay. And then finally, and then yeah, obviously C is also greater than alpha. I'll already put it there. And then the value function, there will be no expectation because everything is deterministic. Okay. Usually this type of problem would be a breeze, right? It would be very easy. But as you can see, I have a lot to talk about, so it's not that easy. So I have this like 1 page for like. It's kind of basics for first year PhD student level, but this is how essentially you verify stochastic control. So I thought that I put some like brief arguments here, and it also tell you what transversality condition is and how you get to your HJB equation. So, well, how would you do it? So first you consider V is going to be your value function essentially at the end. I want to find some kind of differential equation for it. So what I'm going to do, I'm going to look at this function e to the minus delta t V, right? And then see how it changes. So what I'm going to do is, if it was stochastic, I will apply Ito's rule to it, but this is deterministic, so it's just going to be integration by part. So write integration by part for this guy, and then what I would get, and I also add this term, which is essentially my utility, if you think about it, right? So you start with a general C, you write the dynamics of E minus delta T, you add this as well to both sides, and then you're going to get to this integral equation that V e to minus delta T equals this guy equals Vx plus this guy, and this operator is given by this thing. I just like calc 1 kind of question. And then now the point is that if I let t goes to infinity, then this part becomes my utility, so essentially my value function. If you call this optimal value function, this is going to be your objective function essentially. This is the Vx, which I want to compare with this guy. And then if I make sure that this goes to 0 as t goes to infinity, then I can essentially control the size of this compared to that by just controlling this guy. That's the whole idea, all right? So now I need to make sure that this goes to 0 as t goes to infinity for all x that are corresponds to some admissible strategies, and that is called transversality conditions. So if that's the transversality condition holds, then I can let t goes to infinity. Then I can say that if I make sure that this is always non-positive, right, then this is going to be always greater than that. So this is going to be an upper bound for the value function. If, on the other hand, I find a special C for which this is going to be 0, then this would be the value function. And that's how you verify this problem, right? So anyway, so what I want to control the sign of this guy, and that would give me this differential equation, let's say. So it's going to be the supremum of all C. By the way, don't forget the habit formation means C is greater than alpha. The supremum of all C greater than alpha of the C-dependent parts plus the other not C-dependent parts should be 0. So for all C, this should be negative. For one C, it should be 0, and that's how you control. Okay, so now this is now I need to find a solution for this guy. This is the HJB equation. Okay, so what do I do? Well, I'm just gonna optimize first with respect to C. That's kind of easy, but the only difficulty is that you have a constraint here. I mean, not difficult. The only like interesting part of it. So you can actually do the optimization and show it that the optimizer CS star is given by this result. So if this is large, then essentially the optimizer would be just alpha. If this value is small enough, then this is going to be the optimizer. Right? It's very easy. Just take the derivative equals 0 and then see whether that root is satisfying this constraint or not. Okay, that's you get that. But then all these type of problems essentially starts with an ansatz. What is the structure of this optimal consumption? And this is essentially shouting at you what the structure is. You just need to think a little bit about this. So first of all, I will start, I mean, this is how I think about this. Look at this part here, right? At the end of the day, this part would be like, let's say, reciprocal of consumption. So you expect consumption to be increasing in X, right? More wealth, more consumption. Meaning that this part inside, you will accept at the end of the day, this would be a decreasing function of X. So now you can see the condition. So it says that if this is large, means the X is small, you're consuming at the minimal rate, alpha. If X is large, means this is small, you're consuming more than alpha. That's what it means. So it's essentially, it means that there is a critical level of X is wealth to habit, such that if you're below that, you will consume at the minimum. If you have enough wealth, you're above that, it's more than that. So this is going to be your ansatz, right? And then for this ansatz to work, you need to have the correct sign for these ranges. So this is going to give you like a variational inequality type of, and then you can essentially plug in the minimizer here, and you're going to get a free boundary problem with this X star being the critical level, right? So, let's take a look at this. So this is a linear equation piece of cake, right? This is a implicit ODE. Well, I don't know if you still remember how you deal with this type of things. What you would do is you call this a variable, like say phi, and then try to find a differential equation for phi. That's how you solve this kind of thing. And if I look back in October of 2018, I already had this, right? So all I did in the last 2 years is essentially figure out how to solve it. So it's, I mean, the problem I had is that if you keep like working at this, you're missing a point. And the point is, this is under specified. So let me explain. So you have a general solution. You have a C here for this. You have another, let's say C here. So 2 unknowns. And then you have an under, like a free boundary, so 3 unknowns. You have one condition here, which, by the way, the condition comes from this thing. So at x equals alpha, this essentially should be equal. So that's where this condition comes. So you have one condition here. You can give one more condition by making sure that this is continuous or smooth, right? So you have 2 conditions. So you're missing one condition, right? So you're missing one condition. You need to figure out what to do with that. Usually in ratcheting problems, you will get another condition by smooth pasting, but that will not work here because there is no upper bound for X bars. I mean, I don't want to get into details, but the smooth pasting will not give you the extra conditions here. So what you need to think about is actually what is the marginal utility at X under. We naturally assume that's infinity, but it turns out here that's not the case. It depends on the value of delta. Sometimes v prime at X under is actually finite. So that was the missing part I had. So it turns out it's actually easier to apply the Legendre transform here. Usually we apply Legendre transform to linearize something. It will not help us here because if I apply Legendre transform, I still have an xv prime. It's not going to save me here. X becomes u prime, right? V prime becomes y. So it's still going to be, it's still going to have this. But it will help me in the sense that I give name to the marginal utility at X under. I call it y over, right? So usually y over is plus infinity, but now I assume that it's either some finite number or infinity. Anyways, you apply the Legendre transform. You might think it's unintuitive. Now I used to have a free boundary with 1 free boundary. Now it turns it into a free boundary with 2 free boundary. But as I said, it will help you, right? So now you have 2 free boundary. When you use y over, which is again is the marginal utility at X under, the lowest wealth, and there's y0 star, which is the free boundary you had X star, comes from there. And then you have, like, again, 2 boundary conditions. One is for defining essentially y bar, and the other one is the free boundary condition I had there. Yeah. So now my job is going to be how to solve this thing. So let's call this from now on the dual value function. Use the dual value function. Okay. So now how you're going to solve it? You need to make an extra ansatz, because we're missing still a condition. You can still go through that. Now I have 1C, 2C, but now I have 2 unknowns, so 4 unknowns. I have 1 condition, 2 condition, another for a smooth pasting of these 2, so 3 conditions. So I'm still missing another condition. So for getting that extra condition, this is what you need to do. You need to break the situation into 2 cases. For delta large, delta small, right? This is what you need to yeah, please go ahead. I have a question. Yeah.
Do you not from transversality get some condition, or?
From transversality, it will be very difficult to get a condition out of it, because it's going to be a condition around y equals 0, right? And then you will see that actually this is actually easier to go than the other one. I'm sure there's a way to do it, but this is how I think about it, right? So anyways, so let me just explain what this case means. So delta, if you remember, delta was the utility, or maybe I should show it here. Delta is the utility discount rate. Large delta means impatient person. Small delta means patient. So you can wait to consume later. So that's what delta comes in. Okay, so right. So first, consider the large delta case. The answer, the additional condition you need is this: y0 and y bar are equal and finite, right? So essentially what I'm saying is that if you're impatient, you throw away this. This is moot. This never happens. You're always going to be in this case. Translation: this is moot. You never have this. X under is X star, essentially. Translation again, this never happens. So you always consume above the minimum rate. So I'm just sorry about going back and forth. So that's the answers I'm taking for impatient people. And then once you do that, then you have essentially go up. You have two conditions for y bar and y star. If you assume that they're equal, you can solve for y star. Actually, you can show that the y star is going to be this a specific number. X under is the lower like minimum wealth that you need for no bankruptcy. So everything is known here. So once you have the value, a specific value of the free boundary, then everything essentially boils down to a fixed boundary problem, right? So for delta large, you get a fixed boundary problem. Now, where does this come from? Well, I told you about the trick of dealing with implicit functions. So you just call this something. I call it psi of y, and it turns out actually it's better to analyze the inverse of that. So y of psi is the inverse of the psi of y, and then you can show that this always have a solution. What you actually need is a strictly increasing solution, so that you get a decreasing and convex U, which you can invert with the Lejeune transform. So anyways, just want to say how you can actually show that this exists. So you need to kind of analyze the right side, right? So this is the direction fields for two case, delta larger, delta equals. So what happens is that under this like a region, that thing is going to be positive. So you will have increasing solution. So you're looking for increasing solution here. The terminal values start here. So it's alpha minus gamma. You have y star equals this, and then you're proving that there's a solution here. I mean, you can easily show that. This is not a big deal. And then plus, you can actually show this that there's a lower boundary. So there's this function, this guy, that essentially compares with the solution. This is super helpful for verification. So this was actually a lot of technicality was solved by just when I find out that this is the lower bound. You can also show that another lower bound is essentially y equals 0. So essentially the solution exists all the way to 0, which is nice. And then once you have solved that, then you're going to get your U explicitly in terms of psi of y. I forgot to write down psi of y is inverse of y of psi, which exists because it's strictly increased. And then once you have U, right, you can essentially what to say? Oh, okay, so let's go consider the other case. Now, what if delta is small? But if delta is small, the ansatz that you need to take is that y over is infinity. So now the marginal utility at 0 is infinity. So we are back into usual case. But the other free boundary is now finite. So you're going to end up with a single free boundary problem. And then you kind of do the same thing as the previous case, but now the ODE for y would be a free boundary problem. So it's going to have the same differential equation. Is that now the terminal condition is going to be a free boundary condition. So y0 is also. Now, this might puzzle you once you start actually analyzing this, you will see that actually this is not a free boundary problem at all, right? So if I again do the same thing for different value of delta, look at the sign of this side, then I will get this. So essentially what happens is that the region where the right-hand side is positive now breaks into two parts. And specifically, there's this point y naught and psi naught, which I have explicitly in terms of in terms of the market parameters, right? That there are these things split the place where you have increasing solution into two parts. In other words, any increasing solution, you're looking for increasing solution on the domain 0 to alpha to the minus gamma, have to pass through this point. And it turns out that point is a singularity point. There is actually, I can prove that there are two solutions. One is decreasing, one is increasing. I want increasing because of I want some property for u, and there's only one solution. So it turns out that this is not a free boundary problem. It's only one increasing solution, and whatever value it has at alpha minus gamma is your free boundary. So this was very interesting to essentially, it helps me a lot to essentially go through the technicalities. And then once you have this, then you essentially can again write u in terms of y star that you can essentially find here. By the way, this should be y star 0. That's a typo. So and then yeah, you will have two parts, right? If you go back, you have two parts for u, right? This part would be explicit because it's linear, so you can explicit write in terms of y0, and this part would be implicit, and it would be written in terms of this function psi y, which I also find. So now I have a complete solution for the u function. Now what I can do is I have the nice properties as well. I already proved them, so I can invert the Legendre transform. I got V's, the solution for V, and on top of which I can also find the maximizer for C star. Everything is in terms of Y star and psi. And then don't get confused with this J minus X, just the inverse of U prime of Y, which I also have in terms of essentially psi. So, okay. So that's it. So now I have the solution for the free boundary. I also like characterizes the value of the free boundary as well, and also V. So the only thing that left is actually do the like formal verification, right? So I threw away a lot of like details of the verification part. So essentially, you need to do two things. First is you need to prove a transversality, which again, as I said, I think briefly, this type of comparison, this kind of upper bound, lower bound for this case, and lower bound for this case is super helpful for the transversality. So you can essentially show that, not easily, you need to do some estimate, but it's helpful for that. Second thing, you need to show when you plug in C star of X, this guy has a solution and is admissible. But both, like for the admissibility part, you need to essentially dig up a little bit more property of the optimal solution, which I present as the chlorine, right? It's very dry if I want to explain it in text. So let me explain it in a picture. So these are the extra properties that you get. So what am I showing you here? I'm showing you the optimal consumption function as a function of relative wealth. So this is relative consumption, this is relative wealth, right? For two cases, impatient, patient, right? So for impatient, if you remember, X star was non-existent, so it was essentially X under. So there's no flat beat. So you're always gonna consume above the minimum rate alpha. For patient, you're gonna first consume at the minimum rate until your relative wealth hits X star, then you're gonna consume above. Now there is a red graph here. I want to explain what that is. Well, let me go back to the initial wealth function that I have. You can here see if C is large, then this drift term will be negative. You're gonna be decreasing your X. If C is small, believe me that this is going to be positive, and you're going to increase your x. And then the question is, for what value of c this is going to be 0? And then you can see it's just r plus rho x divided 1 plus rho x. So if your c is that, then this is going to be 0 locally. You're not going to change in your x. So now this is what I have here. So for each level of x, this is r plus rho x divided 1 plus rho x. If your c is above this, you're going to be decreasing your x. If your c is below this, you're going to be increasing your x. And now you can just see what am I doing for impatient individual. He or she is going to always be consuming above this level, so he's always be decreasing her x. So in other words, it's optimal for that person to essentially decrease their x all the way to x under. So they're impatient. They don't appreciate having any extra wealth. They just want to consume it away, right? That's what that's what the essentially the x star shows. Now for patient individual, do you remember there was this y star, psi star here? This point that split things, and these are essentially known constant in terms of the parameters. Now these will essentially introduce a x star, c star, right? And that's the point where the red and black meet. So now you can think about it this way. So if your x, if you're patient, if your wealth is above this value x0, you're going to be consuming in a way to decrease your relative wealth. If your wealth is below this x0, you're going to consume in a way to increase it. So in a sense, you want to get to that point. You want to have a relative consumption of C0 and a relative wealth of X0. So impatient people have some idea of where they want to be. If they're above there, they will decrease. If they're below there, they will increase. Right now, I can show you in terms of the actual wealth paths as a function of time. So what I do here is I start with a specific X, and then I solve this OD because I know C0 is going to be an OD. I can just solve it. So numerically, right? So you can see that it is exactly what I said. If you're impatient, you start with a wealth, you're going to consume until your X becomes the lowest possible. Otherwise, you go bankrupt, right? And then your essentially consumption is also goes to the lowest possible. So here you're consuming as much as you can, essentially, right? If you're patient, it depends on whether your wealth, like relative wealth, is above X0 or below it. If you're below it, you're going to increase it to X0. If you're above it, you're going to decrease it to X. And then similarly for consumption, you're going to start with a high consumption, go to 0, or you start with low consumption and go above. And then you can see also, like at the beginning, this guy, because his wealth is below the X star, he would just consume alpha until the wealth level hits the X star, and now it starts consuming above alpha. So we can see everything here. Now I can't translate everything to absolute wealth, and this is the plot. So I said that if I have X star K and C, I can recover the absolute wealth W and C and also Z. I have here, I can explain some stuff here, but let me pass through this. There's some interesting behavior happening, but I want to explain the next slide. I'm running out of time, so I want to stay here. So what this slide shows you is how your consumption changes with alpha. So suppose that, let's see, me and Geshen all have things, so all of our things are the same. Delta, risk aversion, everything is the same. The only difference we have is that I have more addictive habits. I have a larger alpha. Now the question is, if our wealth and habit are the same, am I going to consume more or less than? And then this essentially shows you what happens. So it depends on how impatient we are. If we are essentially patient, right? So you have like three regions. So if delta is less than R, What does it mean? Like, look at the critical value of delta is r plus rho times 1 in alpha. The smallest it can get is when you put alpha equals 1. This could be r. So if delta is less than r, you always, for all alpha, you're going to be in this patient case. And this is what I'm showing here. So I'm showing you the optimal consumption for various value of alpha, but when delta is less than r, so for all the alphas, things will be patient. Now you can see, if me and Getchen are both above our x star, so let's say I am 60, Getchen is 40, right? And our relative wealth is 4, relative wealth to habit is 4. Then you can see we're consuming exactly the same amount. So if you're consuming above our wealth, then we're going to be exactly the same. But if we are, like, let's say it's 2, right? Then I cannot follow Getchen. Getchen can consume at this level, but this is below my alpha, so I have to go above. So in that sense, if you're patient, we're both patiently consuming, then the only thing that matters is whether I can actually follow him or not. If I can't, I will be above. But if not, I will be below. Now let's go to the other extreme where everybody is impatient, right? So here, then I go back again. What is the maximum it can get? So if when alpha equals 0, it's r plus rho. So if delta is greater than r plus rho, everybody will be impatient. And you can see here, right? And then again, let's consider the case where I am 40%, Getchen is 20. And you can see if we can both afford a wealth, so let's say 4, then I will be consuming less. And this is the unintuitive part. A more addictive person will consume less than an addictive person. So that's the message, which is maybe not unintuitive actually. It means, because if I'm more addictive, I need to be careful, more careful. I should not just do as Getchen does, right? So this is also like that. And then there is this mixed case when delta is between r and r plus alpha. Then some people will be impatient, some people will be patient, and then what we say still applies. So impatient people generally consume less than patient people, unless you're comparing two patient people, and then one of them is essentially restricted with their habit formation, in which case it will be consuming more. Okay, so but this is full story. It's just complicated, right? Okay, so I don't think I will have time to go through the stochastic case. Let's do, I don't know how you want to do it. I want to stop here and then have 5 minutes to see if people have questions. If not, I would just say some extra things about this case. So by the way, so let me go here. Yeah. So there are 2 papers. There are the same, like very similarly titled. The clue is one of them has investment in it, and the one with investment is the stochastic case. The one with without investment, just the consumption, is the deterministic case, right? So, yeah.
Okay, great. Yeah, so thank you very much, Bahman. I think Martin has a question.
Yeah, please go ahead. Yeah.
Many thanks for a very interesting talk. So maybe I missed that. So what is the role of gamma for this?
Oh, gamma is the risk aversion.
Yeah, but where does it in this different? It didn't sort of appear, or maybe
because it appears. It appears everywhere actually. So let me see.
But did you come at the end when you had these different regimes?
Oh, right. So so it affects the level of consumption here, right? So that's how it affects. But does it affect the regimes? Interestingly, no. So of course, if I like here, I'm assuming everything is constant. So my gamma is the same as Getchung's gamma, but we have different alpha. So I didn't change gamma and alpha at the same time. I don't know whether I have a graph of a sensitivity with respect to gamma. I need to double check that.
But if you have both the same gamma, less than 1 or greater than 1, doesn't matter. It's the same ordering.
The same ordering. And then there's another interesting part. I don't know whether you did click with you. We usually have ill-posed conditions for gamma between 0 and 1 in my, so if it's 1 minus gamma is your how you parameterize it. Usually gamma near 0 would actually give you ill-posed condition, like expected utility explode, right? Mm-hmm. In this case, in this even the stochastic case, I can prove that never happens. So this is going to be true for all gamma. And the reason is I am taming the wealth. Because I'm dividing by z, I'm taming it. So that was actually an interesting. This is a plus for using this type of dividing by zt, right? It kind of tames the process X. Yeah. Oh, by the way, this is another thing I forgot to say. So most of my like I used Kara utility because I was thinking I would get some explicit things, but now when I mean I've been thinking about it in the last week or so. I'm not using Kara utility for dimension reduction because I reduced dimension before I apply the utility, and then my things are all through kind of analyzing this type of stuff. If I change like a utility with like a general utility, increase in concave utility, this term will change, but the analysis essentially goes through as well. So I could actually write this down for general utility, not just the Kara utility. Mm-hmm. So maybe that's another like cheap paper out there. But anyways, so that's another thing. So what I found is that let me just show you one more picture here at the end. So one of the main motivations for habit formation is to explain the equity premium puzzle, right? Which means that like the premium, the difference between stock returns and bond returns that we see historically cannot be explained just by risk aversion. You need some extra thing, right? So in this case, essentially for a stochastic case, I also show that like alpha is essentially will be increasing alpha, you will be decreasing your stock investment. Essentially, regardless of what gamma you have, so that this was essentially another thing that relates to like this alpha has like effects that doesn't really interact with the gamma that I had. So it's good to separate things, right? So this was interesting as well. Yeah.
Okay.
Okay.
And yeah, thanks. Any other questions or comments? Yeah, Martin again.
Yeah, on the stochastic case, I mean, you already touched on this. And so how does the optimal strategy look like? Is that very different from the Merton one?
Yeah, there are different. So first of all, you would not have the impatient case. You will always, the consumption, let me go on. The consumption process, regardless of the value of delta, it will always be like consume a little bit, and then if wealth is enough, go on. So it's always going to be like a free boundary problem. And the optimal wealth would be first linear, and then this part is nonlinear, but you can show that it's asymptotically linear with a smaller slope. So you will invest more aggressively, let's say at the beginning when you're waiting for your wealth to increase, and then you're just gonna not level up, but you're gonna invest in less. And technicality, if you're interested, I will need to actually solve a free boundary problem. This is not cheap, right? I really need to analyze a system. Now it's going to be a system to